Right. Good morning, children. Welcome to the new session. In this session, we will learn Kirchhoff's second law. This is also known as loop law or voltage law. Shortcut, we say that KVL. So, in this session, we will learn Kirchhoff's voltage law or loop law. In shortcut, we call it as KVL. K stands for Kirchhoff's, V stands for voltage, and L stands for law. What do this law says? See, we studied Kirchhoff first law in our earlier class. Kirchhoff first law says that the algebraic sum of all the currents at a junction or a node is equal to 0. But this Kirchhoff's voltage law or loop law says that the sum of voltages in a closed loop is equal to 0. Here sum in the sense the algebraic sum of, or this can be stated as the algebraic sum of potential drops across various components thence in a closed loop or circuit or mesh, okay, is equal to zero. Sigma V is equal to 0. Here I used the term mesh. What do you understand by mesh? Mesh is the simplest circuit which cannot be split into simpler circuits. This is the simplest circuit, mesh. Okay. So this Kirchhoff's voltage law stated as the algebraic sum of potential drops across various components in a closed loop or circuit or mesh is equal to 0. So here I am using algebraic sum of, means you have to give the sign conventions, you have to follow the sign conventions also. There, while studying the Kirchhoff's first law, the currents that are entering the node is taken as positive and the currents leaving the node are taken as negative. Then here which voltage is taken as positive or which voltage is taken as negative, we will study with a neat closed loop. I will try to explain and I will make the concept simpler to you, okay, with a example. Children, observe this closed circuit. A, B, C, D is a closed circuit. In this circuit, there are three components. One is the power source, that is voltage V, and a resistance R1, another resistance R2 is there. Let I is the current flowing in the circuit. I is the current flowing in the circuit. As for Ohm's law, we know that what is the voltage between R1, between these 2 points, that is, you know that V is equal to IR. So according to that, we can write it as IR1. Next, here the same formula. This is equal to V is equal to how much? Let it be V1 and let it be V2 is equal to IR2. So here the potential difference V1 is equal to IR1, and here the potential difference R2 is equal to V2 is equal to IR2. Are you clear about that one? Across the resistor R2, the potential difference is V2. Across the resistance R1, the potential difference is IR1. How I got it? From the Ohm's law. Now, which one we have to take a positive and which one we have to give the negative sign? Observe this one. You remember, always remember, in a battery the current always flows from positive terminal to negative terminal. This is the direction of the current. You can imagine any clockwise direction. You can move in the loop in the clockwise direction or anti-clockwise direction. See this one. I am moving in the clockwise direction. This is the clockwise direction. So, write the clockwise arrows at various components in the circuit. It means the current is moving like this. See this one. This is the assumed one. Okay. At the battery, you always remember, current always flows from positive terminal to negative terminal. Okay. Now, see this one. The current is flowing. This is the direction of the current. Assumed direction. I am moving in the loop in the clockwise direction. Okay, I am moving. I can move like this also, but I am moving in the clockwise direction. For my convenience, I have taken the clockwise direction. There are three components are there. One is the voltage source V. Another one is another voltage source. What is that? V1, which is equal to IR1. Next, another voltage source V, that is IR2. Now see this one. This arrow, we are moving in the clockwise direction. So this arrow is in the upward direction. The current is also flowing in the upward direction. So this is plus V. Next, observe this one. You are moving along this direction. Observe this one. See this one. This is equal to minus IR1. Next, this one minus IR2. Why? Because the current is moving along this direction. See this one. This is the clockwise direction, whereas the current is moving in the opposite direction. So I have written minus IR1. Here minus IR2. That is equal to 0. The algebraic sum of the voltages across various components 1, 2, 3. These are the three components. V minus IR1 minus IR2 is equal to 0. Okay. This is what is that? Kirchhoff's voltage law or loop law. So very simple. If you are able to draw the clockwise arrows, or if you imagine, if you move in the anti-clockwise direction also in the given closed loop, you can write any one. But the clockwise direction arrows or the anti-clockwise directions, if the direction of the current is opposite to your clockwise or anti-clockwise, you have to give negative sign. Otherwise, you have to give, they are in the same side, same direction, you have to give positive sign. So the sum of voltages of various components in a closed loop V minus IR1 minus IR2 is equal to 0. Okay, right. Start. Let us study the sign conventions while applying Kirchhoff's loop law. See this one. Potential differences is taken positive if we move from negative to positive terminal. Observe this one. I am moving along this direction. I am moving along this direction. So low potential and high potential. When I am moving from this terminal to this terminal, that is low potential to high potential, the potential difference, the sign for the potential difference is taken positive. And if you move in the opposite direction, that is positive terminal to negative terminal, the sign is taken as negative. Observe this one. Next one. Across the resistors, if we move the potential difference, see this one. If we measure potential difference along the direction of the current, okay, along the direction of the current, observe this one. This is the resistor. So I am measuring the potential difference along the direction of the current. So the sign is negative. And see, if you measure in the opposite direction, then the sign is positive. Observe this one. Are you clear about that one? So, if I measure like this in the direction of the current, it is taken as negative. If we measure in the opposite direction to the current, the sign is taken as positive. Are you clear about that one? So, this is sign conventions you have to remember. No need to by heart anything. Simple thing. If you are able to draw the clockwise arrows or anti-clockwise arrows in the closed loop, this loop law is very easy to solve various problems. Okay? Right. Continuation. Children, let us do a sum. Write the potential drops across all the elements in the circuit given. This is the circuit given. Okay, this is the battery, this is the positive terminal of the battery, this is the negative terminal of that battery. So, observe this one, the direction of the current is from positive terminal to negative terminal. So, this is the direction of the current. Now, let us assume move like this A, B, C, D. So, I am moving in clockwise direction within the loop. So, write all the clockwise arrows here at various components. Okay? See this one? I started from here, observe this one. I am moving along this path. 1 minute. See, this is the direction I assumed. I am moving in the clockwise direction within the loop A, B, C, D. See this one. What are the components? How many elements are present? Number of components. First list out. Number of components or elements. How many components are present? A battery is there, and resistor is there, another resistor and another resistor, all together 4. 3 resistors, 1 battery, that is all together 4. Now write the clockwise arrows. Okay, these are all the clockwise arrows. Next, at each and every component, write the direction of the current. See this one, the current is moving along this direction. See this one, this is the direction of the current. Okay, this is the direction of the current and this is the direction of the current. And at the battery, you remember, current always flows from positive to negative terminal. Okay? So, what I did, within the given circuit, I have written 4 elements are present, that is 4 components are present. Okay, next I have written the clockwise arrows within the loop I have chosen. Next one, at each and every component I have written the direction of the current. See this one, the direction of the current is indicated with the white color. Now listen to me. Now list out the potential differences. Here V is there, write down. Next, here as for Ohm's law, this is I R1. This is IR2 and this is IR3. Now see this one, the current is moving along this direction. This is the assumed direction, but the current is moving in the opposite direction. So the sign is, the arrows are opposite. This is minus V. Here this is the direction I assumed within the loop. The current is moving like this and the assumed direction is also along the same way. See this one, this is the direction of the current, this is the assumed direction. See this one. Okay, within the loop I am moving like this in the clockwise direction. Both are in the same direction. So this is plus IR1. Next, this is also, observe this one. This is also same direction. Current and clockwise arrows, both are in the same direction. Next, this one is also in the same direction. See this one. IR3. See this one. Current is moving and the assumed direction, that is within the loop we are moving in the clockwise. Both are along the same direction. So plus IR3. The sum of all these things is equal to 0. Or if I write IR1 plus IR2 plus IR3 minus V is equal to 0. So, applying loop law to the loop. What is the name of the loop? A, B, C, D, A. I started from A and I am moving along this direction and reached this point. A, B, C, D, A. So, the algebraic sum of potential differences, okay, across various components is equal to 0. This is Kirchhoff's second law. Are you clear about that? Make a note of it.